Hey everybody, thank you for joining us. We have Vicky Vergara here and she's going to present today on PG routing. So Vicky, go ahead and take it away.
Hello, everybody. Good morning, good evening, and good night. So today we're going to be talking about the PG routing concepts. And let me share the screen so that you'll see what we're going to be doing. We're going to be reviewing this PG routing concepts page in the documentation. It's been refined like 2 months ago, and we're going to be looking at what are graphs. Basically, my idea is to have some clear idea that PG routing doesn't need geometries. It's all about graphs. Let me increase the font size. So, what is a graph? A graph is a pair of vertices and edges, where the edges are vertices that are connected with each other. And there are different kinds of graphs. So when we look at this definition, we don't see geometries involved. So it's this part that it's very important. Graphs do not involve geometries. And PG routing will be solving graph theory problems. And some of them requires that the edges have some weights, and those weights in PG routing, we call them costs. In PG routing, we represent the graph in the database as follows. With cost column means that there is an edge from source to target. And the weight of it, it's the cost. And when we have cost and reverse cost means that there is an edge from target to source, and the weight of that edge is reverse cost. These two values can be different. So it might be different to go from source to target, maybe just give a value of 5. And from reverse cost, it's from target to source, let's give a value of 3 of the weight, okay? So, graph with costs without the reverse cost column. Here, it's kind of the mathematical definition. The edges are from source to target when the cost is positive. And if the cost is negative, the edge does not exist, okay? And the vertices are going to be the set of the vertices identifiers on the source and target columns, okay? So, let's see how a directed graph looks like when we give source and target costs and the column cost. So let's understand this table. We have an edge identifier 1 that goes from vertex 1 to vertex 2 with a cost of 5, which is this edge. The edge, which ID 2, goes from 1 to 3, but it has a negative cost. That means that that edge actually does not exist. So you can see, for example, that this row basically is adding a vertex to the graph, but it's not adding the edge. The same data, but on an on undirected graph means that there is an edge between source and target, but it doesn't have direction because it's 5. And again, the edge with negative value does not exist. The difference between both graphs, let's try to see both graphs. The directed one, you can go from 1 to 2. On the undirected one, you can go from 1 to 2 and from 2 to 1. In both of these graphs, you cannot go to vertex 3 if you depart from 1 and 2, and you cannot go to 1 and 2 if you depart from vertex 3. 3 is a disconnected vertex. So these graphs, both of them in this example are disconnected graphs. Now, what happens when we have cost and reverse cost? We select the data as follows. We have to select the identifier of the edge, the source, the target, the cost, and the reverse cost. And the edges is going to be the set from that has source, target with this cost when cost is positive, and the edge, target, source with this value also when reverse cost is positive. Otherwise, the edge will not exist. Again, the vertices of the graph is going to be the union of the values of source and target. So let's see with this data. Let's see. What is going on? We're going to have an identifier, an edge with identifier 1 that is going from 1 to 2 with cost 5, which would be this first edge. And we'll also have an edge that goes from 2 to 1 with cost 2. So it would be this edge. For this second row, we will not have the edge from 1 to 3. Why? Because the column cost has a negative value. But we will have an edge from 3 to 1 because reverse cost has a positive value of 4. So that edge with ID 2 and weight 4 is this one, goes from 3 to 1. And finally, the edge that goes from 2 to 3 with cost 7, it would be this one. And there is no edge going from 3 to 2. With this same data, but with an undirected graph, we're basically removing the arrows that were on the other graph. Okay. So for example, if we want to go from vertex 2 to vertex 3, in this graph, in this directed graph, there is no way that we can start from vertex 2 and reach vertex 3. It's unreachable in this directed graph, but going from 2 to 3, it's reachable on this undirected graph. And one thing that we should be looking at is that the graph do not have geometries. Up to this exercise, we haven't seen a single geometry. And that's when we're going to start doing this example. The purpose of doing this example is to really understand that pgRouting does not need geometries, and also that I'm going to be encouraging you on running all the queries that are here. I'm not going to be running them. We're just going to go through. Okay. So we have the wiki example that is taken from Wikipedia, which is this one. It's that algorithm. That graph has been duplicated here. It's Creative Commons. And what the Wikipedia problem is solving is to find the shortest path from 1 to 5. And the graph in the Wikipedia is an undirected graph. It visually looks to have geometries. The moment that we're drawing something on the paper, it has a geometry involved. There's an X and a Y on the paper that we are not evaluating. But there are no geometries really associated to the edges. We can see that this is distorted. There's no way that this is 40 and this is 9 and this is 2. It's kind of out of scale. The drawing is out of scale. Okay. This graph has 6 vertices, mainly 1 to 6, and has 9 edges. The set of edges are going to be from 1 to 2 and 7. Okay, so these edges are the ones that we want to represent in a table in the database. But if we compare this graph and this graph, it's exactly the same graph. It's just drawn differently. And it's still again out of scale. This says that the weight is 2 and this is 9 and the 2 is larger. So this is done on purpose. This drawing is done on purpose because in the graph is going to be an abstract concept. It's not a physical concept. Geometries is a physical concept and graphs are abstract. So let's prepare the database. And when you run it, please create the table, the database, and create the extension of pgRouting. And we're going to create the table with ID, source, target, and cost. Why? Because we have the source, the target, and the cost. We're just going to give it an identifier to identify the edges uniquely. So this is going to be our table that we're going to be creating. And we insert, because this is serial, we insert all the data that was deduced when we were analyzing the problem. Okay. And when we find the shortest path, we're going to run a query, and we're going to have the select statement as what we call it's a inner query. We're going to tell it that we want to find the route from 1 to 5. And let's see what it gives us as result. It tells us that you have to go from the node 1 to 3 to 6 to 5. From 1 to 3 to 6 to 5. it's marked on this blue line. Let's see if that is similar to here when it finds the result. It's from 1 to 2 to 3 and to, no, from 1 to 3 to 6 and to 5. At the end, when it finishes, it will show again that this is the route. And you can find it in two ways, by a sequence of nodes and a sequence of edges. It's going to be edge 2, edge 6, and edge 9. This is edge 2, this is edge 6, this is edge 9. Okay. Now, remember that I mentioned that graphs have two elements. One of them is the set of edges, and the other one is the set of vertices. Basically, starting version 3.3, I think, I'm going to be encouraging the use of the new functions like pgRextract vertices instead of pgr create vertices table. This one will give a more consistent information. So when we extract the vertices using this function, we're going to be using the same query as an inner query, and we will have that vertex ID who has as in edges 2 and 4, and out edges 6 and 7. Note that this set of edges are for a directed graph if the data is considered directed. If it's undirected, then the set of edges that are adjacent to vertex 3 is the union of in edges and out edges. So for example, let's see, vertex 1 has 3 outgoing edges just because of the way I inserted the data. It goes from 1 to 2. But because I'm saying here false, the adjacent vertices are going to be 1, 2, and 3. There is no concept of in edges and out edges when it's undirected. It's only in edges. So let's see this new function. It's a proposed function. Okay, it started to be proposed on 3.3. It exists in 3.0. It's being refined during the evolution of version 3. Depending on the inputs, it will be the columns that are going to be returned. So with the main difference that we have with extract vertices and create vertices table is that we are not longer responsible of the creation of the indexes. Create vertices table created indexes, and it was always looking for geometries. And now with this previous example that we were looking at, we can see that we can use extract vertices without having geometries involved. Normally the data will have geometries if we are using, for example, OpenStreetMap data. So you can call it with the inner queries having geom, and it will tell you the in edges and the out edges. Remember that, consider it as the data being directed, and undirected is the union for the adjacent edges. Okay. Let's see. You can see additional examples. One important thing about these new functions that are going to be replacing the old ones, like this one is going to be replacing create vertices table, is that you can run it, you can make a dry run execution, and it will spit out in a notice the code that you can grab and store in your own function, and you can tweak it if you want to see it like that. Maybe you want to do additional operations because of the because of the type of, I forgot, is if it's a latitude, longitude, I forgot the term. I'm not so used to handle geometries. Anyway, you can grab this code and create your own function and improve it for your own application. Okay. And you can use it to create a routing topology. This documentation has the way on how to create a routing topology. It involves many steps, and the routing topology that is generated using this example on the database on the manual will create this topology. Okay. So I think it's all the time. Questions?
Thanks so much, Vicky. I'm curious. I know you've been involved with PG routing for a long time. I was wondering, do you work with routing outside your work with PG routing? Like, do you do routing stuff? Excuse me?
Maybe it's on chat. Maybe I cannot listen. Let's see. Wait a second. Oh.
Can you hear me?
Yes.
Okay. I was just wondering, like, I know you've done a lot of PG routing work. Do you do routing work in PostGIS, like for a specific application?
Okay. When we're talking about PostGIS, it's, yes, when you are using real world data, it comes with geometries, and you use PostGIS. You use PostGIS to create this abstract of graph of that geometries.
Right. I'm just wondering, like, do you work with some kind of specific real world data? Like, do you do routing for roads, or do you do routing work? Like, how is your work with the PG routing project connected to other work that you do?
Well, basically, I'm a less user of PG routing than many others, maybe. The reason of this is when I arrived to PG routing, there were a lot of bugs because it was like, I'm going to create PGR Dijkstra, and I'm going to use OSN data to test it. And maybe that data, let's suppose that it's in France, because I'm developing something for France. And because the data is not finding a route, I'm going to tweak the algorithm instead of reviewing what is the problem on the data.
Okay.
And there were many problems because that was how pgRouting started to grow. When I arrived, I noticed that, and it's with that big data, without me knowing the structure of Paris, because I live in Mexico,
Oh,
then for me it was fine. It was fine in a route, but that result was wrong because it was building the graph wrong. The data was missing things, maybe, and I was just tweaking the code instead of reviewing the data. So I fixed the code and I said it's not going to happen to me. So everything is like I do it in theory. It should work like this and the results should be like this. And you can see from the evolution of pgRouting on version 2.0, that's when I arrived, it had 80 tests. And right now it has over 35,000 unit tests.
oh wow, that's cool. That's awesome.
Just to make sure.
That's
So I
cool.
don't use it much, but it's mostly used with OSM data. You can use OSM to pgRouting, and it does these basic conversions. Note that it's the latest version of OSM to pgRouting is not using this extract vertices function that I just mentioned, but it builds the graph just like if you go to the documentation of 3.2,
Oh, I
I
see.
think, and if you follow that, it will create vertices table and it creates topology. Those functions are the ones that are used by OSM to pgRouting. It's
Cool.
not updated to this new way of doing things yet. You're welcome to contribute on
Okay. Yeah, okay. Well, thank you so much for talking to us about pgRouting.